Hello, AP Physics C students. Let's have your notes open and your problems in front of you. We're ready to get started today. We're going to continue with the RL or LR circuit, depending on what order you put it in. So yesterday we looked at the idea of we connected the resistance and the inductor in series with a voltage source, and the inductor sort of resisted the flow of charge, eventually allowing the charge to flow normally. But it took some time for the current to build up, and then it took some time for the voltage across the resistor to attain the voltage across the battery. And so it's not exactly right to say so, but it's almost like the same idea as sort of charging up a capacitor. And so it's not proper usage at all because nothing is being charged up. But if we're going to relate this to an RC circuit, it's the same idea as, the charging phase. And so now we're going to look at the discharge phase, which again is totally incorrect. We're using quotes here to say it's discharge, but it's not right either. So here's the idea. Read this notes page, I'll talk about it, and then I'll go through. Okay, so right now the switch is in a position, here we go. Right now the switch is in a position so that the charges can flow over here. Voltage is going to build up across the resistor and then flow back to the battery. So this is the situation we looked at before. Now we're going to switch over to position A. What happens here? Well, the charges were just flowing through the resistor, and the voltage across the resistor is the same as voltage across the battery because it's been on for a long time. And so as soon as move the switch over, the circuit is tricked into thinking that this is almost like a voltage source. It's not a voltage source, but the charges continue to flow, and the voltage across here is going to start to dissipate. Right, so the initial current is still the EMF over R. Again, this is supposed to be capital script E. That's EMF, not capital E, because the voltage across the resistor is the same as the voltage across the original voltage across the battery. And so it's sort of driving the motion of the charges, but this is now sort of discharging. Now, again, it's not the right word to say, but let's go through the equations to see how it relates to that. So again, we're going to use Kirchhoff's loop rule. We're going around this same general direction as the current. So here, the resistor is doing its job. It's losing voltage, so it's delta V equals IR or negative IR because it's losing voltage. Here, we have the inductor losing voltage as well, so negative L di dt. Just do a little rearranging, and this should look awfully familiar. In fact, you know what? Pause the video. From here, you should definitely be able to solve for an equation for a current with respect to time that looks a little bit like the equation we've been doing before. Right? Divide both sides by L, separation of variables. If you didn't do that step, now it's definitely a good time to pause the video and do it from here. Here we go, integrate from I0 to I, because it does start with some initial current being EMF over R, but we sort of tricked the circuit into thinking that there was a voltage source to some current some later time later, and this goes from 0 to t, to our usual separation, or difference in logs is the division. We arrange, you get I equals I0 e to the negative t over tau. Oh, look at that. And so this is the equation we're going to box in for the current in this sort of discharge phase of the LR circuit, where I0 is that initial current, EMF over R. What would the graph look like? You know what? Take a second, sketch out what the graph of the current versus time should look like. You should have no trouble with this one. Here it is. Of course, it's a decay, right? There's an exponential decay. It's all the usual stuff. And again, it's similar to the charging capacitors being discharged, which is why we use those phrases, charging and discharging, which is wrong, but it helps us visualize and connect it. All right. Now, what happens here is that the whole point of the inductor is it actually stores energy. So I'm going to read this slide. I'm going to start to go through developing the equation for the energy stored in an inductor. So whereas the capacitor stored energy in electric field, remember this is a solenoid, and as the current goes through it, it builds up a magnetic field by Lenz's law, and it's going to store energy in the buildup of that magnetic field. So we start with Kirchhoff's loop. We gain we gain voltage through the EMF of the battery, we lose negative IR, we lose negative L di dt. Here, they multiply everything by I and rearrange. Why would you do that? Well, let's take a look. I times E, EMF, that's I times delta V, that's power. I squared R, that's power. That means that this term here must be power, or the rate of change of energy. du dt equals Li di dt. So try this, multiply by d2, and then go ahead and integrate to solve for an equation for the energy stored in the inductor, or the magnetic field of the inductor. Here are the steps. Multiply by dt, integrate both sides. From here it's just integral of I di because L is a constant. And we should be getting U equals 1/2 Li squared. This is the magnetic field energy stored in the inductor with a current I. Or written this way, I like to write U sub L for the energy stored in the inductor, 1/2 Li squared. Over here, this is power. That means the power is Li di dt. Box both those in. Here's our terms. All right, let's just sort of summarize in the quote-unquote charging phase and the quote-unquote discharge phase. All right, so in this phase here, there's no current. We close the switch. Remember, the inductor resists the flow of current, so the initial current is 0. And at that moment, the EMF across the inductor is the same as the EMF across the battery by Kirchhoff's loop rule. There's no voltage across R because there's no current. And then after a very long time, the current gets to its maximum value of EMF over R as if this inductor is not even there. So the inductor actually acts as a wire with no voltage across it after a long time. And then if we allow this to sort of discharge, now the voltage built up across the resistor drives the remaining current. When time equals 0, the initial current is the same as the current that it used to be, and it's sort of built up completely to have that voltage the same as the EMF. Then that current just keeps decreasing. After a long time, of course, the current eventually goes to 0. All right, so let's try some problems here. So take out your packet of problems, take a look at problem 10. Go ahead and give it a shot and come back to see how I solve it. Okay, this is a very, very straightforward problem here. For letter A, the time constant, we know it's going to just be L over R, but since there are two resistors there, it's going to be Req. We, of course, recognize they're in parallel, so you find Req, you put the numbers in and get 0.075 seconds, nothing fancy here. Letter B, notice I don't give the answer because I want to see if you remembered or how you understood what was happening here. What's the current when the switch is first closed? Well, of course, it's 0. Right? When the switch is first closed, the inductor resists the flow of charge, so it takes time to build up the current. This is one of our boundary conditions for an LR circuit. Part C, part 1, we're just using this equation we just developed here, where EMF over R is the initial current. So you just put it in, get 2.63 amps, nothing fancy. For part 2, there's actually two different ways to do it. So here's one way. We can use the definition for the EMF across the inductor, negative L di dt. So we take this equation, we differentiate with respect to time, put the numbers in, and the inductance. However, we could also say that the resistors, the equivalent resistance drops voltage from IR, this is really Req, and then whatever is left is what's the voltage drop across the inductor, right? So a gain of voltage through the battery is 9 volts minus whatever is lost here. Whatever is left is just the voltage across the inductor. And so by one method you'll get 6.89 volts, the other way you get 6.90 volts. Obviously they're the same thing. Feel free to try both. See how you like it. Part 3, literally just application of the equation 1/2 Li squared. And part D, just put the numbers back into the equation. Here we're going to have 90% of the current. This is the maximum current here, and solve for the time. So a very straightforward problem, just getting used to the equations. All right, so go ahead and try problem 11. I will tell you there is a typo because I was changing some numbers. So if you just fix it right now, in number 11, part A, part 3, the correct energy should be 0.313 joules. So go ahead, pause the video, try all problem 11 on your own, then come back to see how I lead you through it. Okay, so here we go. Starting with part A, this is the situation where S2 is open, S1 is closed, so we're quote-unquote charging up the circuit, and so the current eventually, after a long time, is the full current there, the EMF over the equivalent resistance, only being one resistor. Part 2, of course, the voltage drop across the inductor at this point. Remember, it just acts as a wire once it's fully charged, right? There's a wire there, so it's got no voltage drop. And then here's the energy, again, the 0.313 joules, as I told you, the correction. All right, now in the next section, this switch is open, the switch is closed, and now it's just the LR circuit, so the discharge phase, you want to think like that. It'd be useful to find the time constant at 0.0208 seconds, so you don't have to keep doing the calculation, although if you did that, that's fine as well. And it's real simple, you know, the initial current is just going to be 2.5 amps, because again, it's as if this resistor it absorbs all the voltage from the battery, it's running the current the same way it was, so it's just EMF over R, just 2.5 amps. Part C is just an application of this equation with the current that's decreasing. This is just the voltage across the resistor, nothing fancy. This is just an application of the power dissipated by the inductor. For part D, I want to see what you do, so I'll do this as an exercise for you. I'm going to ask you to submit a picture of it to see how you sketch out the voltage versus time graphs for both the resistor and the inductor. So I'm not going to give it away. All right, here I want you to skip ahead to problem 13. Read that. I'll give you a couple starting hints, and I think this is something you can definitely do on your own. Okay, so the starting hints here. I want to remind you the definition of inductance is magnetic flux over current. That's a good place to start. And I will give you your end goal. In the end, we're looking for an expression for the inductance for the solenoid to be mu naught n squared AL. So take some time. You should definitely be able to do algebraic manipulations to solve for this equation.